Welcome to EPG Pathshala. We are looking at a series of lectures in computer science. So, we are looking at computer networks. In today's module, we will be looking at multicasting. So, we have looked at various aspects of IP protocol and we have looked at unicasting related issues that are supported in our IP network. So, what we will be looking at today will be on multicasting. So, we will look at what is the need of multicasting and overview of multicasting, and then we will look at how group management is done, the IGMP protocol which is used for group management, and then we will look at routing and one of the protocols used for routing, which is DVMRP. Okay. So, what do we normally mean by multicasting? Multicasting is essentially one person transmitting and many people listening to it. So, it basically facilitates group communication. So, we talk about one to many. Now, one to many could also mean broadcast, but that is not what we mean when we talk about multicast. Broadcast is open to all, whereas multicasting is open to a particular group. So, a radio station broadcast is actually a one to many, but that is more of a broadcast scenario. Transmitting news, stock price, if you are doing it only to a particular group of people who are interested, then it becomes a multicast scenario. Software updates to multiple hosts, again would become a multicast if you are doing it to a particular set of hosts that need the software update. Okay. So, that is an example of one to many group communication. You can also have many to many group communication, as happens in the case of multimedia teleconferencing, online multiplayer games, distributed simulations and so on. So, you can see that in all these cases, which are very common applications as of today, support for doing the routing of sending the packets, forwarding the packets in an efficient manner becomes very important, especially given today that we have many multimedia related applications, many multiplayer games which are all again heavily loaded in terms of the multimedia data that they need to carry, both in terms of audio, video and other data. So, you can see that there is a lot of requirement to support these kind of applications. There is a requirement to support multicasting in an efficient manner. That is the reason why we need to be looking at what kind of support exists for multicasting in the IP networks and how actually these things work. Okay. So, if there was no multicast, so let us look at that scenario. So, what would happen if there was absolutely no multicast? In a situation where one source needs to send it to a group of people, that source will need to send a separate packet with the identical data to each member of the group. So, it would mean multiple unicast packets that will need to be sent. So, obviously, this will lead to a redundancy in terms of consuming more bandwidth, and this redundant traffic will also not be evenly distributed. You will find that it is concentrated near the sending host, because from the sending host many packets have to be transmitted and from there they may go to different destinations. So, as they go to different destinations at different locations, it may not cause too much of a traffic, but near the sending host you will find that the traffic becomes very heavy. So, this is definitely not an easy thing to handle, it becomes a bottleneck. Second thing is that the source will also need to keep track of the IP addresses of each of the members of the group, and the group can be dynamic. So, keeping track of a group at the addresses of the members of the group, especially when the group is dynamic, can become a very challenging issue. So, this is this tells you that without multicast what will be the problems that you will have. So, it also tells you what exactly multicast should therefore handle, should provide you a mechanism to do all these things in an efficient manner, right. So, what is the kind of multicasting support that we have currently in the IP network? So, if you look at that, first of all we have a multicast group addressing mechanism which is supported in the IP networks, both IPv4 and IPv6. We know that in IPv4 class D addresses are considered to be as multicast group addresses. So, we have an addressing mechanism to specify an address for a group. So, you do not have to remember individual names or individual addresses of the members of the group. So, you can specify just the group address. So, that is one thing that we have. Second thing, there are protocols available as part of the TCP/IP suite that we have to support both group maintenance and routing and multicast routing. So, if we look at how exactly multicasting will take place in this IP kind of a scenario. So, the way IP multicast model has been set up is basically to cater to many based transmission, again based on multicast groups. So, if you look at this, what would typically happen is that every group will have its own IP multicast address, and hosts which are members of a group receive copies of any packets which are sent to that particular group's multicast address. And a host can be in multiple groups, and a host can join and leave groups, and any source can send packets to this multicast group. In fact, IP does not even have any restriction in terms of whether a source has to be a member of the group in order to send package to that group. The source can actually be any source and it could send to this multicast group address. So, this is the basic structure that is supported in IP. Okay. So, to send a group to each member of the group, what it would have to do is that it will just send a single copy of the packet addressed to the group's multicast address. So, it will be a single IP packet, but the IP packet in its source IP address will have the address of the source, and in the destination address will have the address of this multicast group. Okay. Now, the sending host does not need to know the individual unicast IP address of each member. So, it is the same IP packet, only thing is the address, the destination address happens to be that of the multicast group. So, that is the first facility or first support that we have. Okay. Okay. And we also have support for a one-to-one multicast service in IP. Though the original IP's multicast support is meant for many-to-many multicast, it has also been supplemented with additional features in order to be able to also support one-to-many multicast. So, in order to do one-to-many multicast, we are talking about what we call as source specific multicast. So, that is a receiving host could specify that it belongs to a particular multicast group, and it could also specify that it would like to receive packets only from a specific sending host. So, this is referred to as a source specific multicast. So, you have packets coming into that multicast group which a host is interested in receiving because it belongs to that group, but it is also interested in receiving packets only from a particular source. So, that becomes a source specific multicast situation, and that is supported in the there is a support for this also in the IP framework. That is, when you look at the multicast related protocols, they have support for the source specific multicast as well. And the many to many model is in that sense is referred to as a any source multicast. So, you talk about SSM as source specific multicast and any source multicast as a many to many model, anybody could be the source. So, this becomes a proper group kind of multicast scenario. Okay. So, what are the basic requirements for multicast? So, we said we need an addressing scheme which is already provided by IP. So, next thing that we need to do we said was group management and routing. So, these are two things that we will be looking at now. So, group management essentially has to take care of the following. A host should be able to join or leave a multicast group. So, it should be able to signal to join or leave a multicast group by communicating with its local router using some specific protocol. So, we need a protocol to do that. So, in IPv4 the protocol which takes care of this group management is called as the Internet Group Management Protocol, IGMP. In IPv6 similarly we have multicast listener discovery protocol or MLD which is used. Okay. And to support multicast routing, basically the routers will have to take the responsibility for making multicast behave correctly with regard to the host. So, we have two protocols which are very commonly used here, which is DVMRP, which is a distance vector again based on the distance vector protocol extended for multicast routing. And then we have PIM, which is a protocol independent multicast routing protocol. So, these are two commonly used multicast routing protocols. We will be taking a look at this in our course. So, let us look at the group management first. So, if you look at group management protocol, we have IGMP. In fact, there are two additional versions, IGMP v2 and v3 that are used for this. So, we will look at v2 a little bit in detail and then look at what extensions are there in v3. So, our IGMP protocol essentially is a router host protocol. It is meant only for the host to talk to the edge routers, okay, and supported by RFC 2236. So, it is used by the IP hosts to report multicast group memberships to the routers. So, the hosts have to inform the routers that they are interested in receiving packets which are meant for a particular multicast group. So, the router then will have to use that information to communicate with the multicast routing protocol, so that it is able to receive the packets meant for that particular group. Okay, that is the router's job. Now, in the router, in order to talk to the host, the router will request information from the host and the host will respond to find out which groups that they belong to and what is the information they are interested in. The host may also send unsolicited information, that is even without the router asking for the information. The host may send the information to the routers. Okay, so, all these will have to be supported as part of the IGMP protocol. Okay. So, if you look at a router in the context of IGMP protocol, there are basically one of two roles that it could play. One is what is called as a querier and the other is a non-querier. A querier is the one which is responsible for sending queries to the host and getting the information from the from the host. A non-querier is like a silent observer. So, it is also looking at whatever is happening, but it is not doing this job of querying, because we do not want too many people querying. If there are 2 routers connected to a single network, then one of them will be the querier, the other will be the non-querier. The one which normally the method used to choose the querier out of the 2 is that the one with the smallest IP address becomes the querier. So, a querier typically informs, it kind of when it broadcasts some information saying I am the querier, the other querier, other router which is also sitting on the same network will listen to that. So, it can compare its IP address with the IP address of the packet that it receives, and if it finds that the other one has the smallest IP address, the other one, it lets the other become the querier and it remains as the non-querier. Otherwise, this becomes the querier and the other becomes the non-querier. Okay. So, the querier is the one, is the router that is going to be talking to the hosts. Okay. So, this is what happens now. So, the routers will hear the query messages and make the entries. So, what the querier will also do is it will periodically send a general query to solicit some membership information. So, what we mean by a general query is that it is sending a query to the hosts that are there. So, it is normally sent to again as a multicast group address to the address of 224.0.0.1, which is called as the all systems multicast group. So, it is sent to this address, a general query is sent, and when this query is sent, the host will have to respond to this query. Okay. So, when a host receives a general query, what is it expected to do? Normally what it does is, it does not immediately respond, it delays for a random amount of time. It delays for a random amount of time varying from 0 to maximum response time. Normally it has a timer which is set for this purpose, it will start a timer. So, when the timer expires, so its random time expires, then it will send the report. So, the maximum response time for which it can delay the reply is normally specified as part of the query message. So, the router is expecting reply messages to come within that amount of time. So, that is specified over here. So, once this timer expires, the host now will send a report saying that it is interested in a particular group membership, right, that it belongs to a particular group, and it sends it with the TTL value set to 1. Now, why TTL value set to 1? Because we do not want this packet to go beyond the router, beyond the first hop. So, it is meant to go only up to the first router that it is connected to. Okay. So, this use of TTL being 1 is a very interesting aspect that is used over here in this protocol. Okay. Now, another thing which does is, while it is waiting in this random wait that it is doing, if it finds that there is another host that has already sent a report with the same group information, so then it stops the timer and does not send any report. So, you can see that if there are multiple hosts which belong to the same group, on receiving a general query, only one of them will actually end up sending a report, and the others who hear that other report need not send any response. The reason they do not have to send a response is, all that the router needs to know is somebody is there on this network who belongs to this group, and as long as somebody is there on this network who belongs to this group, multicast packets will anyway be sent to this particular network. So, that is all the information that is required. We do not have to flood the router with multiple responses. So, that is the reason why this random wait is used. Okay. Now, similar process is used even if a host receives a group specific query. Now, we talked about general query. In a general query, you are asking for information like, does anybody belong to any multicast group? In a group specific query, the router has a very specific question which says, does anybody belong to this particular multicast group? So, the multicast group address is specified and you request for information about that particular group. So, this is the second step that you have. Now, when the router receives this report, what is it expected to? It basically will add the group being reported to its list of multicast groups, okay, and it will set a timer for the membership to a particular interval called the group membership interval, and within this group membership interval, if no reports are received, then it will delete this entry, okay, and periodically basically it will send out a query. When it sends out a query, periodically when it sends out a query, it expects the responses to be received, which tell you that the host belong to some group. So, if no group membership information is received, so then it will quietly delete that entry from its table. Okay. So, when a host joins a multicast group, what it would normally do is it will send an unsolicited report, that is, without waiting for a query from the router, it can send an unsolicited report as soon as it joins, so that the router becomes aware of the fact that there is somebody here who belongs to this particular multicast group. Okay. So, this is the third thing that happens. Okay. So, this is about joining the group. Now, we also have to talk about how members leave the group. So, when a host leaves a multicast group, what will happen is that what it will do is, if it was the last host to reply to a query, That is, when it received this request from the router, if it was the one which had responded to the query, then it should send a leave group message to the all routers multicast address, indicating that it is leaving that particular group. Okay. So, when a router receives a leave group message, so what does it do? It will now send, so somebody is saying that I am leaving this group, right. So, when it receives that leave group message, what it will do now is, it will send a group specific query, right, periodically again every last member query interval times, okay, for that amount of time, to the group to that network. Now, why does it do this? It is basically to query the network to see if there is anybody else who belongs to this group who is still present on the network. Now, remember that only one person would have sent a report saying that we belong to this group, but there may be other people who are there who have not sent their reports. But now this person who has sent a report saying that he belongs to the group is now saying that I am leaving the group. So, we also need to find out if there are other silent members of the group. So, which is why the router on receiving a leave group message cannot just quietly assume that there is nobody in this group, but now has to send a group specific query message. Now, when it sends out a group specific query message, again the same process will take place, that is all the hosts which belong to that group, when they get that message, they will again wait for a random amount of time and one of them will send a reply. If nobody sends a reply, it means that there is nobody there who belongs to that group. So, if no reports are received by the router for some amount of time, right, which is called the last member query interval time, then it assumes that there are no local members, then it can remove that particular entry from its table, that there are no members now for this multicast group. Okay. So, these are the basic steps that we have in terms of how you join a group and how you leave a group. So, we will take a look at a simple example of what exactly happens. So, let us say this is your multicast router which is connected to many nodes here A, B, C, D, let us say. So, let us look at what happens. So, the first thing that the multicast router does is it wants to find out if there are members to any groups, right, in its interface. So, what it does is it sends out a query message, a general query message, and to ask the various routers. So, that is what it will do. So, it sends out a query message. Now, on receiving the query message, all of them have received the query message. Let us say A, D and E belong to some multicast groups. A belongs to a group called 224.1.1.1, whereas both D and E belong to a group called 224.2.2.2. Okay. So, now obviously, they have to send their responses, right. So, what will they do now? Now, each of them will, before sending the responses, will wait for a random amount of time before sending the report. So, let us say each of them waits for different amounts of time. Okay. So, D is waiting for 10, E for E is the one which is waiting for a shorter amount of time, let us say. Okay. So, E's timer will expire faster. So, E sends its response. Now, when E sends the response, by the time A also has his timer is also expired. So, that also sends a response. Okay. Now, D meanwhile, it would have received that response which was sent by E, and since it belongs to the same multicast group, so what it does is it need not send any response. If you saw in the animation that we just looked at, both A and E would have sent responses. D did not send a response to the router. A belongs to a different group, so it has sent a response. E belongs to a different group, so that response is also gone. Okay. So, now on receiving all these things, let us look at what the multicast router is expected to do. So, now it says okay, these two groups have members, so let me add them to my list. So, I will remember both these in my memory, that is I will put them in my table. Okay. So, now let us say somebody wants to leave the group. Okay. So, let us say for instance, D decides that it wants to leave the group. Okay. Now, what should D do? D basically is looking at whether it was the one which sent the last report. Now, D was not the one which sent the last report, right. So, which means it can leave quietly. So, if it was the one which had sent the last report, then it will have to send a leave message, but since it did not send any leave report, it can quietly leave the group. Okay. Now, let us look at, for instance, A wants to leave the group. Okay. Remember, A was the only one that belonged to that group, right. So, he was the one who had sent the report earlier, therefore, he will send the leave message and that leave message goes to multicast router. Now, on receiving the leave message, we know what the multicast router is expected to do, right. So, what is the multicast router expected to do now? It will say okay, let me find out if there is anybody else who belongs to this group. So, it will send out a packet saying a group specific query asking if anybody belongs to that group. So, now what will happen? On receiving that request, you will find that there is nobody who belongs to the group. Remember, only A was the only one who belonged to that group. So, now what will happen? Our multicast router now will set up a timer, will be waiting for a response to come within this timer amount of time. So, it is waiting, and while it is waiting, if there is no response received at all. So, what will happen when the timer expires? Now, it can identify that there are no hosts which belong to this group. So, it says okay, I guess there is no one in this group, right. So, then it can now remove that entry from its table. So, it removes that entry of 224.1.1.1 from its table, and with that the that group has been removed. So, it will still have the other group, the DE group, right, because E is still a member of this. So, that entry will still be there, but this entry will be removed from the group. So, this is basically how the IGMP V2 joining and leaving of the group takes place. Okay. So, if you look at the message formats which are used for this, a very simple message format basically. You have a type in the message which tells you whether it is a membership query, whether it is a general query or a group specific query, and then there is a maximum response time field, a checksum field, and then a multicast group address. The type will also tell you whether it is a membership report or a leave group message, okay, all that will be specified over here. Now, this maximum response time, we saw that that will be used whenever you have a membership query message. So, basically the amount of time that it is the router is expecting to wait for before it expects a response, okay, and it will be set to 0 in other messages. Checksum is your normal 16 bits once complement checksum that we are so familiar with by now, and this group address, multicast group address is used whenever you are sending a group specific query. The address that you are looking for will be specified here. So, general query, this value is set to all zeros. So, this is essentially how the IGMP V2 works. If you look at the V3 protocol, there is additional support here for certain other features. One of them is source filtering. So, what we mean by source filtering is that a receiver may request to receive packets only from specific source addresses. So, we talked about this as one of the requirements, right, in multicasting. So, this support is specified in IGMP V3. So, you can select source addresses either as using either an include flag or an exclude flag. So, what this means is that you can have two flags, either an include mode or an exclude mode. As you can say, I want packets only from this particular source, or you can say I do not want packets from this particular. So, you can exclude a packet from a source from the from what you would like to receive, or you can include a source in what you would like to receive. So, both these things are possible. Okay. So, these are some of the things that are provided in IGMP V3. So, V2 and V3 put together give you a very interesting nice protocol for managing the groups. Okay. So, the next function we need to look at with respect to multicasting is multicast routing. Okay. So, we know that a unicast forwarding table in a router will indicate which is the link to use to forward a unicast packet meant to a particular IP address. So, now to support multicast, what we need to do is we need to have multicast forwarding tables, which means you need to have destination addresses as multicast addresses, and you need to know which are the interfaces through which it will have to be sent out. Remember, it may not be a single interface through which it has to go out, but it will be multiple interfaces through which it will have to be sent out, because you may have group members belonging to different networks which may be on different interfaces of a router. So, that information will have to be specified. So, unicast forwarding table in general, we can say collectively all the forwarding tables put together, they specify a set of paths, right. So, whereas a multicast forwarding table collectively will specify a set of trees. Now, why a set of trees? Because we will see that the path to go from a source to multiple nodes, multiple receivers of a group would actually be in the form of a tree. So, it is a question of constructing what are called as multicast distribution trees, which become important in multicast routing. So, multicast routing is all about finding this multicast tree starting from a particular point to reach all the nodes which are there in that group. So, that is what we need to understand, how this is basically set up. So, as I said, the problem statement, if you look at for multicast routing, the goal is to find a tree or trees connecting routers which have local multicast group members. Okay. So, if you take this this set of routers, okay, so you can see that we are talking about routers which have group members, and we are also showing routers which do not have any group members. For instance, this one here, this does not have any group member. Wherever you have a red colored host, that indicates that it belongs to a particular group, let us say. Okay. So, you could have what is called as a shared tree. When we talk of trees, there are two types of trees that we talk about here. One called a shared tree. A shared tree is the same tree will be used by all the group members, right. So, for all group, so if you take this one for instance, this router, this router, this router and this router are all connected by means of this particular tree here. Take this as the root, from here to here we have a path, from here we have two branches, and from here you have a branch to this particular router here. This router which is not part of the group is not part of our tree. Similarly, this link is not required because you already have a path to reach these other routers which are important for us. Okay. We could also have what is called as a source based tree. So, what we mean by a source based tree is that depending on which is the source, you could have a tree set up for sending packets from that source to the various members of the group. So, in this case, for instance, you can see that there is a green color one which corresponds to this node being the source. So, if this was the source, you can treat this as the root of the tree, and you can see that from here you have a different path. So, you have a different tree here. If this was the source, then you have the red colored tree, right, which shows that you have path from here to here and so on. So, you can see therefore, by having source specific trees, right, you will actually have multiple trees. So, which is why we do not say just finding a tree, but we say finding trees if necessary, because if you want to source specific routing, then and you want to in fact we will see that multicast basically supports both these options. It supports both what is called as a source based tree and also supports a group shared tree. Okay. Source based tree is used in the DVMRP protocol. So, essentially we have one tree per source, and so we construct shortest path trees from each source. So, that is what happens in this case. In group shared tree, which is used in the PIM protocol, the protocol independent multicasting protocol. So, what happens here is that the entire group uses one tree. So, this may be either a minimal spanning tree constructed using Steiner tree, or it could be a center based tree. You will find that actually it is a center based tree. In fact, PIM has two modes of operation, one in which it uses a source based tree and one in which it uses a group shared tree. So, we will look at PIM later. We will look at this DVMRP protocol. Okay. So, this distance vector multicast routing protocol is essentially an extension from the distance vector routing protocol, which is the RIP protocol that is used for unicast routing. So, it is kind of closely tied to this RIP protocol. So, it is kind of dependent on the RIP protocol for doing its job as well. Okay. So, what it actually does is it constructs, as we said, a source based tree, right. So, per source a tree will be constructed, and it will provide the shortest path between the source and the receivers, all the members of the group. Okay. And the algorithm it uses for that is referred to as the reverse path forwarding algorithm or RPF algorithm. So, it is very interesting to see how the RPF algorithm works. Okay. So, there are basically three steps used in this reverse path forwarding algorithm. The first step is referred to as reverse path broadcast, okay, RPB. Okay. Then we have something called a pruning step, where you prune to a reverse path multicast. You prune a broadcast tree to become a multicast tree, and then forwarding is done unidirectionally on this multicast tree. So, you can see what is happening here. So, what we are actually doing is we are starting off with a broadcast mechanism from a source. You basically broadcast all over the place, that is your reverse path broadcast, okay, to reach all the nodes that are there in the group. And then if a particular router does not have members who belong to the group, you need not be forwarding packets on that, right. So, you can prune that particular branch of the tree which connects that router to the source. So, that is a prune step. Once the pruning is done, you actually have a nice tree which is actually connecting up all the members within the shortest path. So, then you start forwarding packets along that path or along that tree as such. So, let us look at this a little bit more in detail. So, we said we will first do a broadcast on the reverse path, right. So, what do we mean by this reverse path? So, when a multicast packet is received, you forward the packet on all of its outgoing links only if the packet arrives on the interface that is also the interface of the shortest path back to the sender. So, this back to the sender is what you need to note here, because this is what gives this name of reverse path broadcast. So, what are we doing here? You broadcast the tree, broadcast the packet. So, when a particular router receives a packet, it checks whether it is receiving that packet from an interface that it will use to send packets to that particular source. So, if it receives it from that interface, then it will forward that packet to all of its outgoing links. Remember what we do normally when a router has to do forwarding, right? It will receive it on one port, send it out on all the other ports. So, before sending out on all the other ports, it just checks whether the port on which it came in corresponds to the path back to that particular source. So, if it is on that path, then it will do the forwarding, otherwise it will not do the forwarding. Okay. So, you make sure therefore that the packet is not duplicated, that is if you have already sent a packet on this particular from this particular router or from this particular interface to the other interfaces, you will not send it again. Okay. If it is not coming on this particular interface, then we will discard the packet. Okay. So, you forward only if it is received on a particular interface, and if it is not received on that interface, then you discard the packet. Okay. So, this you can see is our reverse path broadcast mechanism. So, a quick example to take a look at that. So, if you see this, so this is our source. Okay. Let us assume that we have members over here connected to RB and to RF, okay, to these two routers. So, let us look at what happens now. From source, when the source sends the packet, RA receives it on this particular interface, will now forward it on to this interface here to RC, RB and RD. Okay. Now, when RC receives a packet on this particular interface, you can see that this is its path to the source. So, it will take it from here and forward it on other 3 links, right, that is towards RE, RD and RF. But when RD receives it, when it receives this packet from RC, it will discard that packet. Why will it discard the packet? That is because this packet is not coming on an interface through which a packet which was meant for source would actually come from. So, remember, source is to come from, let us say RA is the shortest path to go to the source to RD, right. So, RA is on that path. So, if I receive something from RA, I will take it. So, the packet that comes from RA is taken and forwarded on this, right, whereas the packet from RD will not be forwarded, it will be discarded. What is interesting to note here in this example is, this packet which is forwarded by RD when it comes to RC will also be dropped by RC. Why will it be dropped by RC? You can easily figure that out. That is because it is coming again on interface which is not the shortest path to the source. Already it has got a packet from RA. So, this packet which is coming again now will also be a duplicate packet, right. So, on 2 counts this packet will be dropped, right. So, this packet coming from RD is dropped, but already the packet from RA now has been forwarded to RE and RF. Okay. RF has that will automatically now forward it to the corresponding receiver over here. Now, RE will forward it to RG. Okay. Now, RG does not have anybody else to forward it, so it will just drop that. Okay. Now, similarly here RA would have forwarded to RB and RB again will send it to the destination node. Okay. So, this is our the reverse path broadcast mechanism, and where you forward and where you discard is what we need to note in this particular step. The next step we said is the pruning this reverse path broadcast tree to make it as a reverse path multicast tree. So, if you look at this example here, you can see that RE and RG actually do not have any members, right. So, you actually need not forward packets to this group. So, now RE and RG will have to say that they do not want to become part of this tree because they do not have any members who belong to this group. So, they need to just send back a prune message saying that these branches can be pruned out of this tree. So, that is what is the next step. So, prune to RPM tree. So, this is done by routers that do not lead to any members. Okay. So, they will send what are called as prune messages to the upstream routers. And how does a router know whether it has any members or not? That it knows because it has run the IGMP protocol. So, it will know whether there are members to that particular group. So, if there are no members to that particular group for which it has received packets, it will send the prune message. So, in this example therefore, we can see that RG sends a prune message here, RE in turn will send a prune message to RC. Similarly, RD also does not have any members belong to the group. So, RD will also send a prune message here. So, we have seen that. So, these two, so RE, RG and RD can now be removed from this tree, right. So, what we will end up with is a reverse path multicast tree. So, which connects the source through the shortest path to the 2 members that belong to this group. So, you got this path here through RB to this, through RC and RF to this particular node. Okay. So, once this tree is constructed now, the tables at RA and RC and RF are set so that when a packet is sent with this is received with this particular for this particular multicast group address, it will be forwarded on these interfaces. So, at RA when it is received, it will be forwarded on these 2 interfaces, 2 interfaces through which it will be forwarded. RC will forward it on 1 interface and so on. So, this is basically how the reverse path multicast tree will be constructed. Okay. This mechanism of DVMRP, it has certain drawbacks, it also has certain benefits. So, one of the drawbacks of course you can see is that the first packet has to be flooded, and you also need periodic prune messages to be sent or state refreshes to be sent, right. So, that is also something which is important. And in fact, not only do we prune, we also need something called a join, because if you have pruned a particular branch, and later there is a new host which joins that particular router which is interested in this particular group. So, then you will also have to be sending out a join message, right. So, that will also be something which will be which has to be looked at. So, you have to maintain routing state per source group, that is because for every source we need to have this information, per source comma group pair you have to maintain the state information. Of course, benefits are that it guarantees efficient delivery and it is very easy to implement, because you can see that it is a very simple process that actually needs to be done at each of the routers. Okay. So, that is those are the benefits and these are the drawbacks. So, other problems that we have with the DVMRP protocol, which is the reason why they are not as popular as other protocols that have come after that, are essentially that these work very well mainly for densely represented groups. So, when you have a network where there are many members of the group, so which means that your multicast is almost similar to a broadcast mechanism, that is you have many branches and you have many hosts which belong to those branches, right, of the tree. So, in those cases you will find that the overhead is really not too much, but when you have a sparse tree you will find that there will be lot of messages that need to be sent, lot of prune messages that need to be sent and so on. So, it becomes a little inefficient. Okay. And there is a large amount of state information that is stored both for forwarding and for the prune state information. So, these are again, as we said, major drawbacks, and another reason is that it is not scalable. So, for these reasons we typically do not use DVMRP, but we go in more for other protocols. Typically we use the PIM protocol, which is the protocol independent multicasting. So, we will be looking at that in the next module. Okay. So, to summarize what we have looked at in this module are the following. So, we saw what is meant by multicasting. So, we saw what are the requirements for doing multicasting. So, we also looked at how the group management protocol works, what is required for the group management protocol and how the IGMP does it in a very efficient manner. And then we talked about multicast routing. So, where we looked at what is called as the flood and prune technique, the DVMRP technique, which is also referred to as the flood and prune technique. Remember, we just flooded the packets and then you prune so that you get your reverse path multicast tree. So, we also saw how that works, and we also looked at some of the advantages and disadvantages of that approach. We will next be looking at the protocol independent multicasting approach. Thank you.